Okay, so now that we know what is stride, padding, convolution, let's observe. Now let's see that how did this field of CNN evolved over time. Before 2012, the architectures used for image categorization and image classification, they were just simple MLPs. And after 2012, AlexNet was introduced. And let me just tell you about the challenge called the ImageNet challenge, which basically is that several teams used to participate in that. It consists of a data set which had 1.2 million training images and there were 1,000 categories. So teams used to compete like who would get the highest accuracy, who would get the lowest error rate. The metric used for this competition was the top 5 accuracy. So which means that if I have a model, does the correct prediction of the image comes in my top 5 predictions of the model? If yes, then it is true. It's a true value, right? And so let's go on to AlexNet and let's see what is it. So first of all, in 2012 there were major constraints in the memory. GPU didn't have much memory, so this model was split into 2 GPUs, 2 graphic cards. And the error rate on ImageNet for the ImageNet competition was 16.4%. It had various convolutional layers, max pooling, FCNNs, and ReLU nonlinearities. Now let's move to the calculation part of it. In the first layer of convolution, as you can see, there were 3 channels, and the height width, which is the spatial resolution, was of 227. In the first layer, the filter used was of kernel size 11x11. We used a stride of 4 and padding of 2. And in each convolution, we don't only use a single filter, we use multiple filters, right? Each capturing different patterns. Like say the first filter captures edge at some angle, the second filter captures some color blob or some variations in color along the image. And we apply these kernels on local spatial resolutions, as my teammates just explained to you previously. And now let's go on to the calculations. Now in most of the cases, the kernel depth or the kernel channel is same as that of the input image. In some cases, it can be different. Like if you have coded in PyTorch, we use argument called as groups. So we can vary the channels of the kernel as well, but usually it is as same as the input image. So after we perform this convolution, the formula for getting the final resolution is given by this: W minus K plus 2P divided by S plus 1, where K is 11 in this case, P is the padding, which is 2, and S is the stride. So by this formula, you can see that we got a final output, which is the activation map of spatial resolution 56x56 with number of the channel dimension as 64, because each filter gives us a 2D grid of activation map, and because we have 64 filters, we get 64 activation maps. So the final dimension of the activation map is 64 cross 56 cross 56. Right. So let's see how much memory does this activation map consume. Okay. So in this section, right. So the final dimension, as I told you, it's 64 cross 56 cross 56. So this equals to 2,704, and we assume that we use FP 32 floating point. So each element in the activation map consumes 4 bytes. So as per this formula, we got 784 kilobytes of memory. Now if we check how many parameters were in this convolutional layer, it is 64 cross 3 plus 11 plus 11, because each filter has channel depth of 3 and resolution of 11 cross 11, and there were 64 filters. So we multiply all of these to get this number, 23,000 approx. And now we can check how many floating point operations were performed in this convolutional operation. It basically means that how many multiplies and adds were there in this computation. And let me help you visualize this. The size of the activation map was 64 cross 56 cross 56. And each element in this activation map was computed by the dot product of the filter and the local spatial part of the input image. So it is basically equal to the dimension of the activation map and the into the dimensions of the filter. So it comes out to this, which is 73 megaflops, which is a huge number. Yeah, similarly, we can compute these calculations for every layer. So we have convolution and pool, then convolution, then pool, then it repeats, right? For the pooling operation, let me just explain the calculations for that as well. So pooling layer does not have any learnable parameters. We just have to get the max or the average value of the local spatial part. So the output channels are same as the input channels, which is for the second layer, which is the pooling layer. Second layer, it remains as 64. So we can, for the same formula, we can calculate the after the pooling layer, what is the resolution of the output image, which is by this formula is 27, And for the flops, as I said, parameters is 0. You can check the table. For the flops, it's like if you have a 3x3 max pooling filter, it's like comparing each element in that 3x3 window and getting the max of it. So we get the maximum value from the 3x3 window. So using this formula, we can get the number of flops as well. Okay, so next slide. Yeah, so after multiple iterations of pooling convolution, we flatten the whole image for further classification, for the final classification, because all these convolutional pooling was operated on the was the main idea behind this convolution pooling was to preserve the spatial structure. And now that our final application map has captured what patterns does our image has, we can just flatten it and we can add an MLP to get the final classification. All right, so we have flattened this, which is 256 cross 60 cross 6 cross 6, which gives us 9216 dimensional vector, as you can see here, and then we have layers of MLPs, and we can also calculate the number of parameters and the memory consumed and the flops for this. And in this table, I have to just specify that I have not included ReLU. It is there in between, but I have not included here. And batch normalization, which is very important for gradients to, for easy convergence, did not exist in 2012, so it's not here. Now, interesting trends. These trends actually are very common to every architecture of CNN, and you can refer to this table. As you can see, like for this diagram first, the memory consumed in the first convolutional layers was very high. See this table, 784, 182. The memory consumed, but the convolution operations were very high, and number of parameters was actually very high in the MLP layers. And again, see here, parameters are 37,000 compared to just 23K or say this 590K in convolutional or pooling part. Number of flops were kind of more for convolutional as well. And again, see this table, 100, 125 megaflops compared to 38, 17 megaflops. And this trend is actually common to every architecture of CNN. We would see in the upcoming slides. Now, in the next year, ZFNet, it's a new architecture which is introduced in the ImageNet challenge, and it was basically AlexNet, but improved version of it. As you can see, the major changes were that in the first convolutional layer, the filter was changed to 11 cross 11 stride 4 to 7 cross 7 stride 2. So the basic significance of this is that we don't want the downsampling to be very aggressive. We want it to capture more local patterns, and that. But also the spatial resolution of the feature map had increased, which would mean more memory, more flops. So yeah. So along this evolution of CNN architectures, you would be able to see that as we increase the computation, as we have more parameters, the accuracy increase, right? So the value for this was 11.7. Yeah. So next was the VGG. Now AlexNet and ZFNet was mostly trial and error. There was no certain design rules that we have to use this dimension of kernel or this stride or this pooling. There were no fixed values, and there were like no set of rules that we could use to design better architectures. So, but VGG hadn't introduced some design rules. Let's just check it out. All convolutions were 3 cross 3 stride 1 pad 1. All max pool are 2 cross 2 stride 2, and after every pooling, double number of channels. So in this network, we introduced some stages, as you can see in the diagram as well. Stage 1 was conv pool, and stage 2 was again conv pool. Stage 4 was conv 4 times conv and then pool, and similarly in the 19 layer as well. So now let's check it out. Let's just check how is this design rules beneficial for us. So suppose we have two options, which is one convolutional layer of kernel size 5 cross 5. It does not change the channel dimension. As you can see, C is same as C in the output as well. The parameters here are 20. The formula for this is 25 C square. How? Because the kernel is 5 cross 5, and we have C number of kernels, and the channel dimension of the kernel is also C. So C into C into C into 5 into 5 to 25 C square. And the number of flops is 25 C square H into H to W, where H and W are the spatial dimension of the input image. We have this first option, okay? Then second option was introduce two convolutional layers, but of lower kernel size, say 3 cross 3. In this option 2, the parameters were reduced to 18 C square, as well as the flops to 18 C square HW. And how you would ask me that how is this option 2 are the same thing? There's something called deceptive field. Suppose we have a set of convolutional layers, right? So this, in the last activation map, this cell was derived from this 3x3 area, because the kernel gives a single value by performing the dot product and the summing all the values. So this was derived from this 3x3. And then this 3x3 was derived from this whole 5x5. Okay, and this 5x5 was derived from this whole 7x7. So basically, the deceptive field is that, like in this cell, the deceptive field for this is 3x3 for the last layer, and for the initial layer it is 7x7. So basically, we can say that this cell summarizes the whole 7x7 input image, something like this. So both the options have the same deceptive field, but the parameters of the flops decreases a lot. And for the max pooling part, where I just tell that after pooling double the channels, how is this useful? Again, as you can see that as we have double channels and then we perform convolution again, memory is decreased, parameters are decreased, but the flops are same. So we get a beneficial advantage over memory and parameters. So that's why we use this technique. Yeah. So here it is just compared. We have just compared AlexNet with VGG. So as you can see that more memory consumption, more parameters, especially more flops have given us good results on the ImageNet challenge. It is 7.3 here for the VGG, as you can see. So that's comparison. Okay, the next is GoogLeNet. So now, all the architectures that we saw previously were basically trying to improve accuracy by increasing parameters, by increasing number of flops computation. But GoogLeNet tried to just deploy these models on edge devices as well, because on edge devices as mobile, and here we have to, the major challenge was to decrease the number of flops and parameters so as to make the model fit on the mobile devices. So here some techniques were used in GoogLeNet. This is the diagram of the first initial layers. You can see the calculations are shown, and basically in this block, which is highlighted here, like I told you in the first chart of this trend, that most of the memory was used in the convolutional part. Most of the flops were used in the convolutional part. So here they have tried to downsample aggressively. As you can see that they have used a slide of 2, pad of 3, a lot of higher slide and pad, which downsamples very aggressively and just reduces the number of computations of the memory usage. As you can see in this comparison also, memory used by the GoogLeNet was 7.5 megabytes compared to VGG 16, which took 42.9 megabytes. Similarly for parameters and flops. And this was another module introduced by GoogLeNet, which is called the Inception Module. Now, all these slide and padding, filter size, number of filters are just hyperparameters. We have to decide them before training, and we don't have a good idea that, yeah, this is the correct, this slide of 2 or slide of 3 is the correct or the most optimal parameter for slide variable, right? So this was introduced, so it has just parallel branches and it incorporates every filter size so as to get a flavor of all the possible filter sizes. And this 1x1 bottleneck is just used for like changing the channel dimension and maintaining the spatial resolution. So yeah, the next technique that we used in GoogLeNet was of global average pooling. Now, what does this mean is that we, in the interesting trend table, we saw that parameters were mostly consumed by the MLP part, right? And so global average pooling, what it does is that suppose our output activation map has a dimension of 64 cross 128 cross 128, right? So we have like 64 grids of 128 cross 128. What does GAP, which is global average pooling, do is that it averages over the grid. Like if we have a 64 cross 128 cross 128, after this pooling operation, we get 64 cross 1 cross 1. So for every grid, we get a single value, right? So it highly decreases number of parameters used and the memory consumption as well. Okay. The next was very important, auxiliary classifiers. Now, it's a problem with deeper networks, and that is the problem of vanishing gradients. Because as we backpropagate, and the concept of chain rule, we have to multiply the gradients to get to the initial layer, which is like if we have a loss function here in the top, we have to get to the bottom of it, we have to multiply the gradients along the way. And if the gradients are very small, and so the multiplication is very small, so these initial layers are not updated at all. So to solve this problem, what it did was they introduced auxiliary classifiers. So in between the network, they introduced some like small classifiers, like loss is also being taken here and here in these blocks, and it basically helps to maintain the gradient, I would say. Yeah. So after GoogleNet, batch norm was introduced, which further enhanced the accuracy of further models. Okay, so this is the last network I would discuss, which is ResNets. Here also we saw that as we made the models deeper and deeper, the accuracy decreased. Instead of increasing, which was a trend before, it decreased. And it was because of the problem of vanishing gradients, as I told you earlier also. So here there were two types of architecture used, 18 and 34. So the main technique used here is of res connections, which is basically, say, you see the pointer here, like we have got a gradient here during backprop, right? One of the path of the flow of gradient is this, which is conventional. But in this case, it also flows along this path, the curved part. So it adds to it. So it maintains the gradient as well, and it uses the problem of vanishing gradients. So yeah, that's all which is required. And yeah, so as we make the networks deeper, we have to ensure that the accuracy is at least as good as the shallower network. So we should ensure that the model at least learn the identity function, which basically means that at least if the weights of these intermediate convolutions are set to 0, it still gets the value of this previous input from this path, right? So it does not loses the accuracy, and it is at least as accurate as the previous shallower model. And here we have compared how what error rate different architectures got on the ImageNet challenge. So as you can see, the ResNet got the lowest error rate, which is 3.6. And that's all from my side, and thank you.